Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support me and this channel by liking and subscribing. It means a lot and it really supports me to make more interesting math videos for you to enjoy. Now in today's part 31, as promised in the last video, we will take a look at a real-life application of differential equations. Please recall from the last video, a differential equation is in the format of dy over dx equals to the multiplication of two functions in terms of x and y. And it is called separable if we can write everything in terms of y in one side and everything in terms of x on the other side of the equation. Very important thing is that dy and dx have to be on different sides of the equation, and they also both have to be in the numerator. And finally, in order to solve this differential equation, we can simply take the integral of both sides, compute them, and get a function of y completely in terms of x, which is our end goal. Now, let's take a look at the dead body example, which uses differential equations. In this example, we're going to use a differential equations founded by Newton, specifically Newton's law of cooling, which can also apply to warming, of course. It states that the rate at which an object's temperature is changing at any given time t is proportional to the difference between its temperature and the temperature of the surrounding environment. So that means we can express this as dt capital, which denotes temperature of the objects, over d small t, which means time, equals to negative k times t, again temperature of the objects, minus t0, which is the surrounding environment. Now this negative k here is just a constant of proportionality. It is negative, which indicates that an object's temperature is falling, thus Newton's law of cooling. So now to the example. Police discover a dead body at 6 a.m. in the morning in a room maintained at 22 degrees Celsius. So this is the two information. T0 is equal to 22 degrees Celsius and body was discovered at 6 a.m. When discovered, the temperature of the body was at 30 degrees Celsius. 3 hours later, meaning at 9 a.m., the temperature of the body had dropped down to 26 degrees. So again, T0 does not change because the room is maintained at 22 degrees Celsius. And finally, it states that at the time of death, the body was assumed to be at 37 degrees Celsius. Now we have all of the information we need and we can plug them into our differential equation. This what we got here is actually a separable differential equation. So that means we put everything in terms of capital T on one side and everything with small t on the other. Once we have separated them, we can take the integral of both sides in order to solve it. The integral on the left-hand side would simply give us a ln of t minus 22. And on the right-hand side, since k, or negative k, is just a number, the integral of it is going to be negative k times t, and of course, plus c. And finally now, we can get rid of the logarithm. On the right-hand side, please recall that e raised to the power of c can simply be rewritten as a capital letter A. At this point, we can actually find the value of both a and the value of the proportionality constant k using the initial conditions that were provided for us. Now, I just want to make one thing clear. T equals to 0 means midnight. So if they say at 6 a.m., in this case, t would be equal to 6. So what we get with the initial condition, at 6 a.m., the temperature of the body was 30 degrees. So I plug that in, t minus 22 is equal to a, raised to the power of negative k times 6. And then I can also use the other initial condition, which states that the temperature of the body dropped down to 26 when it was already 9 a.m. So 26 minus 22 is equal to A times E raised to the power of negative 9k. Simplifying the left-hand side of both equations, we get a little simultaneous system of equations, which we can solve simply by dividing. If I divide one equation by the other, what I get is 8 over 4 is equal to a divided by a simply cancels out to 1, and we have e to the power of negative 6k divided by e to the power of negative 9k. And this can be simplified to 2 is equal to e to the power of 3k. Please recall the laws of exponents. If you have the same base and you have a division, the exponents simply subtract each other. So negative 6k minus negative 9, same thing as plus negative 9k, and you get positive 3k. And finally, you can solve this, because k is just going to be equal to the natural log of 2 divided by 3. So now that we have the proportionality constant, we can actually use it to find the value of a. We can use either one of the equations that we have up here. Let's say we use the first one with the negative 6k. So I plug in my proportionality constant into the first equation, and this then can be simplified even further. I can then rewrite this equation as 8 is equal to a times e to the power of ln from 1 over 4. And then e to the power of ln will simply be cancelled out, and what we get is 8 is equal to a times 1/4. And this implies that our a is equal to 32. So now that means we can rewrite this answer that we got here with all of the known numbers. So now, with the rewritten equation, we can leverage the last piece of information that was given to us in order to find the time of death, specifically t. It was said to us that at the time of death, the body was assumed to be 37 degrees. So all I have to do is solve this equation right here for t. So first, I subtract both sides from 22. Next, I can divide both sides by 32. Next, it would be really nice to get rid of this negative sign in the exponent. All I have to do on the left-hand side is simply flip the fraction. And then next, to get rid of the exponent, I can leverage the natural logarithm. And finally, in order to solve for t, I just have to divide both sides by the proportionality constant ln2 over 3. And this right here would be our answer, only it is in exact form, so we have to put it into a calculator and find that it is 3.28. So if t is equal to 3.28, that means the person died approximately 3.28 hours after midnight. And I can tell you that 3.28 hours after midnight is approximately at 3 a.m. and 17 minutes. And just like that, using differential equations, we were able to find the time of death with a few extra pieces of information. And differential equations can be applied not only to find the time of death of bodies, but also to model population, whether it's increase or decrease, and much more. So for now, this is it about separable differential equations. In the next video, I will show you another type of differential equation that we need to know how to solve. In other words, it is not going to be separable anymore, so we need to employ another method. So I really hope to see you there, and have a nice day. Bye!